Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Matteo Cerruti, Annika Rudolph, and Maria Petropoulou with us today. Hello, all.
Hi, everybody.
Hi.
Hi.
Okay, Matteo, let's start with you. What's your geolocation? Where are you at?
So right now I'm calling you from Paris, France, where I'm a professor at the Paris Cité University and the Astroparticle and Cosmology Lab.
Very cool. And it is late February, February 19th, I think, 2026 as we record this. And is there any snow on the ground in Paris?
No,
No?
it was not a very, it was a very rainy winter, but it was a snowy wind.
Okay, very good. Very cool. And Maria, let's go to you. What's your geolocation? Where are you at?
Yes, so today I'm talking to you from Athens, Greece. I'm currently an assistant professor at the National and Kapodistrian University of Athens at the Department of Physics.
Cool. Well, if there's no snow in Paris, there's probably no snow in Greece.
No, not at all.
Oh, we're in a snow-free zone, so we have one more to check out here. Let's see. And Anika, what's your geolocation? Where are you at?
I'm at the German countryside, like 1 hour away from Berlin,
Okay.
Germany. It's very snowy here. I just went for a run in the forest,
Oh,
and we
nice.
had an extremely snowy winter with minus 14 degrees, etc. Yeah.
Oh, yeah. No men and everything. Let's see, and I'm in Phoenix, Arizona, and we definitely do not get snow in the winter. We cool off a little bit, but we warm up pretty well in the day, and this is what drives all the Canadian snowbirds to come to the Southwest during the winter. Although we do pay for it in the summer when it gets a little unbearably hot. So very cool. Anika, and let's go with you. What do you like to do for research?
So I'm not active in research anymore.
Mhm.
I went off to work as a software engineer in the industry
Oh, cool.
2 years ago.
Uh-huh.
Before that, my main interests were gamma ray bursts and the numerical modeling of those, with a focus on leptohadronic processes, combining photons with neutrino non-observations, actually, not
Nice. Mhm.
observations.
Mhm. See? It's like riding a bicycle. You never really forget. And Maria, how about you? What do you like to do for research?
Yes, so I'm mostly interested in studying high energy emission from different astrophysical environments, mostly AGN jets.
Yes.
I also worked a little bit on gamma ray bursts, which is my second favorite, let's say, topic. And I also do some work in particle acceleration processes through numerical simulations and modeling.
Nice. Beautiful. And Matteo, what do you like to do for research?
Well, I'm also active in the gamma ray community, and in particular in well, let's say gamma ray from jets in general. So in particular, AGN jets.
Mhm.
So as we will discuss today, one of the topic or things I like to do is to make numerical models, and so try to understand how jets radiate. But I'm also very active in the observational community. So I'm
Mhm.
one of the TV astronomer. So I work with Cherenkov telescopes, including
Oh,
one which is not far off from Phoenix, the Veritas telescopes
correct.
in
Yep.
Tucson.
I was going to say, I was wondering if we had all theorists here, if we actually had some observers.
Well, I'll send out. Let's say.
Very good. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A comprehensive hadronic code comparison for active galactic nuclei. And Matteo, Annika, and Maria, take us away.
Okay, so thanks a lot. I'm gonna start and introducing the article, and then we will share a bit the discussion. So yes, this is a work which, as the title of, we hope it's clear. The goal is to really make a comprehensive comparison between radiative codes. So of course we are the three of us here, but it's a work of many people.
Good.
I think you will see later that we show the comparison for 5 codes. So the first 5 authors are actually the people who represented these codes. So in addition to us, there is Marcus Bircher from South
Huh?
Africa
Yep.
and Stamatis Statopoulos, also from Athens.
Yes.
We also show an analytical comparison. So this work was
Oh,
mainly
cool.
Fotini, Economo,
Uh-huh.
uh, other authors. And then we have all the collaborators, so Stavros, Anton, Shan, Susumu, Apostolos, Kota, Anita, and then Joshua, Xavier, Walter, and Andreas Zech. So I think as introduction, we should also say that this is it's a long paper that took many years to
yes.
be done. So we started working on this in 2019. I think the first we had was a quite long time ago. But I think it will be clear once we start presenting the paper.
Very cool. So that was a great shout out. That was a great shout out.
Good. Okay. So if we let's start with introduction and let's try to understand what is the goal. So what do we want to do? Yeah. So as one of the, let's say, one of the big questions we try to answer is indeed the study of cosmic rays. And we do know that, let's say, direct observations of cosmic rays are very difficult to do because they are charged particles. Yes. And so it is very difficult to do source identification directly with cosmic rays. So one of the best ways we have, or we think we have, is to have indirect observations. So we try to find, let's say, alternative messengers, and these are photons and neutrinos that are produced by these cosmic rays. Yes. So what we call hadronic in the title of the paper too, what we call these hadronic interactions are basically interactions of these cosmic rays with something else. And so we try to observe the outcome of these interactions. So we study we study gamma rays, we study neutrinos, and we're trying to infer the properties of these cosmic rays. I'm with you. This is, I think, one of the, let's say, main goals of whole high energy astrophysics. Of course, it has the big open question to say, okay, are the gamma rays we are observing really coming from cosmic rays or not? And so this is the very famous in our field, leptonic versus hadronic discussion. Indeed. So every time you get gamma rays, you always have, okay, who is producing these gamma rays? Are these the electrons? Are these the protons? We don't really know. Of course, the smoking gun that we are hoping to have are these neutrinos. So if we detect neutrinos together with photons, then we are basically certain that what we are observing is hadronic. Correct. Yep, I'm with you. Cool. Now we go back to 2019. So why we started in 2019? Because finally, in the last decade, we now have neutrinos, thanks to the IceCube detector in Antarctica. And then in 2018, exactly, there was this very famous hint of association between a neutrino and gamma rays. And so this is telling us that in this case, an AGN, a Blazar, could be cosmic ray accelerators. And so all of our groups, actually represented here, started modeling the source. And so we try to understand if we can, from the models, infer something on the cosmic ray spectrum at the source. Problem is, at that time, all the codes were private, and we couldn't really compare our results. So this is why in 2019, once we published these first papers, we decided to sit down together and to see, okay, can we actually try to have a fair comparison of our results and make sure if everything agrees, and if it does not, why? And so it took us some time, but the result of these long discussions is all here in this 30 pages paper that we put out to the community, together with the Zenodo. So all the files are in a Zenodo directory, so everybody can actually have a look at it. Beautiful. So to finalize this, and then we will go in the details. So why this step was not available? So why we didn't do this before? So the main reason is that hadronic codes or hadronic processes in general are intrinsically challenging from a numerical point of view, mainly because you need to simulate proton-photon or proton-proton interactions. And so this needs some kind of numerical framework. We do not have simple analytical approximation that you can test the result with. So somehow, you can benchmark a bit your result, but the details, at some point you need to trust your code. So this is why we think that this paper is somehow filling a gap and giving to the literature like as extensive as possible check of 5 different codes in the literature and try to see where we stand.
Cool.
So this is the introduction, and it took us, as I say, 5 years to do that. But now I think we can present the results. So I let my colleagues continue.
Yes, so I will be talking about one Blazar emission models just to set the scene for the readers and the audience. Just to say, however, that this, to complement what Matteo said beforehand, that this has been a very interesting experience. And it was a very nice collaborative work, which was initiated, it was impromptu. So we sit down, as Matteo said, and we started working together from distance mostly because of the COVID pandemic, among others. But it was a very nice experience after all. And I think... I hope that also the readers will enjoy reading the paper. So I hope so.
Yeah.
So let's talk about blazars, and just to say a few things about the Blazar emission models that we will be using as the framework, the modeling framework. As it was mentioned beforehand, AGN, active galactic nuclei, are candidate sources for particle acceleration, cosmic ray acceleration, and neutrino production. So one subclass of AGN, which are called blazars, are the most, let's say, luminous sources or the most persistent sources of electromagnetic radiation in the universe. And actually, blazars are a subclass, as I mentioned before, of jetted AGN. So these are AGN that launched relativistic plasma jets from their nuclei.
Okay.
And in particular, when we are observing blazars, the line of sight of the observer actually is very well aligned with the axis of the jet. In other words, it is very similar to looking down through the barrel of the jet.
Yes.
And because this plasma that emits is relativistically moving, all the radiation that is being produced in the jet is Doppler boosted to the observer's frame. So all the emission coming from relativistic particles in this plasma is dominating all the other components that we typically observe in AGN environments, like the disk emission or the emission from the broadline region and the infrared rays and stuff like that.
Right.
So in that sense, blazars and the emission, modeling the emission of the jet is a unique laboratory actually, because we observe non-thermal radiation and then we try to go back and infer the properties of the radiating particles and try to say, okay, are these electrons or protons? Are these cosmic rays or not?
Yes.
So the basic characteristics of blazar emission is that they have a very extended spectral energy distribution that extends from radio wavelengths up to very high energy gamma rays, sometimes up to hundreds of GeV or even TeV energies.
Yep.
And despite this very wide range of emission, their spectra are kind of boring, one would say. They're very simple in a sense because they have two broad components. One is speaking typically at lower energies, in optical up to X-ray energies, and the second one peaking in the gamma ray band.
Yes.
And typically in this leptonic versus hadronic dispute that we are having in the community, we are disputing the origin of this very high energy component, the one that peaks in the gamma ray band. I mean, we are pretty convinced, and the community is convinced now through decades of observations, that at lower energies, radio up to X-rays, the emission is coming from the synchrotron radiation of relativistic electrons.
Yes.
And also there is observational evidence for polarization in the radio band as well. Also in the optical, and more recently in X-rays with the IXP instrument.
IXP, yeah.
So at least this is kind of settled, but the question is what powers the gamma ray emission, and if this is coming from cosmic rays.
Right. Okay.
And brings me now to the description of the model, which is very simplistic in a sense, but it contains all the necessary elements to explain this broadband multi-wave, the broadband non-thermal emission.
Okay.
So currently, what we call in our field one-zone models is the following. We consider that all this emission that we observe is basically coming from one active region in the jet, a localized region,
Okay.
which is described by a few parameters. So one key parameter is the Doppler factor that relates to how fast this active region is moving within the jet and also accounts for the viewing angle. The other parameters that describe this active region are the size of the region, the radius, and the other one is the magnetic field strength. What is the average magnetic field that permeates this region?
Delta R and B. Okay.
Now moving, these are the three parameters that describe, let's say, the properties of the region. And then we moved to the parameters that describe the distributions of the relativistic particles.
Okay.
So if we consider that we have in this region accelerated electrons and protons, and these are accelerated into a power law distribution, so an extended distribution in energy, in particle energy, the key parameters that one needs in order to compute the radiation is the energy range of the particles, so the minimum and maximum, the power law slope of that distribution,
yes,
and of course the normalization that tells us how many particles we have in the source.
Okay.
And thereby, in typical hadronic models, one-zone hadronic models, we have three parameters for the source. We have 4 for the electron distribution and another 4 for the hadronic distribution. That's it.
I'm with you.
So
Good.
now I'm giving the floor to Annika.
Sure. Yeah, I think the next step here in the paper is that we directly describe the codes, but I would like to take a step back and have a little reflection about the physical processes that all of these codes actually implement.
Cool.
So as Maria already mentioned, we have a magnetic field, and then we have the assumption of accelerated particles. And Matteo in the beginning already mentioned that the simple model are the leptonic ones. So let's think quickly about what are these leptonic scenarios that we could have. We have electrons that are accelerated in a magnetic field. So we have synchrotron radiation. Then we have a photon field, and we have those electrons, which means that the photons can inverse Compton scatter on the high energy electrons.
Yes.
Okay. And obviously we have synchrotron self-absorption, so the reverse process. And at very high energies, 2 photons may annihilate into a lepton pair. These are the purely leptonic processes.
Photon.
Everything that's just related to a charged particle in a magnetic field, of course, not only electrons can do that, but also protons that are similarly accelerated can undergo the same processes in the end. So we could have synchrotron emission from protons. We could have inverse Compton scatterings with protons in principle.
Yes.
But in addition to these processes, hadrons can do a little more.
Okay.
We can have, for example, beta Hadley pair production on the field of a nucleus where that one, where photons are produced when electron pair is produced.
E plus E minus,
electron positron pair is produced. And then we have protons and neutrons who can produce pions, and those pions subsequently decay into muons and neutrinos. What all particles can do is just escape, or they could just cool adiabatically due to the expansion of the whole thing.
Good. Yes.
So roughly speaking, those are the processes that all of these codes are somehow trying to implement.
Very good.
That's quite it's quite a few. Now the code that I'm representing is AM3.
Okay.
I think it's for astrophysical multi-messenger modeling. Yeah, that's 3M. And it's a time-dependent code, which means that for each point in time, we solve the energy distribution of all the particle species that there are.
Okay.
Photons, electrons, neutrinos, protons, all of them.
Yes.
This is formulated in the form of a differential equation. The first one that we actually see a bit more up, exactly
Equation
that one.
Yep.
So in differential and time, we have cooling processes. We
Yes.
have the upper one, the cooling is the gamma, because
Yes.
it's
Gamma dot.
yeah.
Yeah.
This is energy loss processes, because the gamma here represents the
minus
energy.
sign too. Duh. Okay.
Yeah, and it's minus sign.
Okay.
You're so right. We have everything that's related to escape. That's the second term. And then, of course, we could have injection coming from either particles directly being injected because they are accelerated, or they could be injected because they are newly produced in the processes that I just mentioned beforehand.
Right. All sources. Okay.
A lot of sources. And of course, each particle species has such a partial differential equation associated with it, and they are all coupled because the interactions of the one produce the other, the one cool on the other, etc., etc. So it's a system of coupled partial differential equations, and it's notoriously hard to solve, I would say, and computationally expensive.
Yes.
As I think it's very common, we do this in logarithmic energy space.
The range.
To have, the broad range, and also, to be able to properly solve it. AM3, what I would mention about it is that it has a fixed energy grid, whereas you can define the time step. The user can define the time step. And we have a very particular approach for the solvers. For the low energy, we just properly solve the partial differential equations, etc. But for the highest energies, where you have one dominant cooling process, we apply a simplified analytical solution. And this will significantly speed up the computation simply.
Okay, I'm with you there.
Cool. Then, of course, we give all the details of which papers we follow for the implementations, but I think this would be up to very interested people to read up on. I'm not going into the details here.
Do it implicit. Fine. Okay, I'm with you. Yeah.
Yes. I think with this, I'm done with the introduction of AM3. Who's next in introducing their code? Maria, probably, right?
Maybe. If it goes alphabetically, I think is the next one.
Which code should we go to?
Okay, code Athena then.
Athena. Okay, let's see what we got here. Athena, yes, 3.2.
Yes, so I'm representing the code Athena, which, as you might guess, it has been developed by people from Athens.
Yeah.
It was first developed by my former PhD supervisor, Apostolos Mastichakis, in the 90s, when it was let's say, the era where people started writing codes in order to actually simulate gamma rays coming from AGNs. Back in the 90s, it was the first discoveries of these sources in gamma rays. Cool. And then it was co-developed by Stavros Dimitrakoudis, who is also a co-author, and by myself.
Cool.
Of course, John Kirk has been a developer of the first version of the code. So the idea is very similar to what Annika presented. So again, we write the same equation as equation 1 in a slightly different form, in equation 4. So I'm not going to go into, again, describing each term because it is exactly the same. It has the same physics and ingredients as Annika presented for AM3. I want only to stress that because these are, as Annika mentioned, non-linearly, these are equations that are coupled to each other. So you can imagine that you have at least 5 stable particle species in your code, electron, and positrons, protons, neutrons, and photons. And then these are coupled through these different source and energy loss terms. So this makes this kind of codes very ideal for also calculating and treating nonlinear problems. And this is very different with respect to codes used in cosmic ray propagation, for example, because people who are interested in cosmic ray propagation from their sources to Earth, they simply have a beam of particles that they interact with a bath of photons or whatever else, and you simply produce your secondary particles, and you don't really care how these interact with the parent particles. And this is what makes this particular type of codes that we are discussing today very interesting, because they're tailored for modeling the source physics and not the propagation physics.
Yes, and there are some famous examples.
So, in terms of, let's say like a sanity check, when we write this type of codes, at least in Athena, what we do is that we want to compare how much energy is being lost from one particle species due to an interaction, and how much energy is gained by another particle species due to the same interaction. And this is what equation 5 describes, basically, which is what we do for each process in the code. We want to establish on the left-hand side of equation 5, you can see the energy lost by one particle species due to the process J, and what enters into another particle species. And we want these two terms to be equal to each other in order to have energy conservation. Obviously, because we are actually working numerically and we have a discretized energy grid, we don't expect to have, let's say, 100% energy conservation in the codes. But just to give a sense to the audience, I mean, we typically have 1 to 10% variance between these two sides of equation 5. But it is typically up to the user if they want to actually use impose a stricter energy conservation. They can decide to renormalize one energy. For example, if you compute the energy loss of one particle species, and then you decide, okay, I'm going to renormalize my energy injection rate to match exactly the energy loss rate.
I'm with you.
So that's actually what we are trying to do in order to make sure that we don't have the leakage of energy or a surplus of energy. Besides that, also very similar to, just to mention something about the proton-photon interactions, which might be somehow different implemented in our code compared to the others, is that for process number 9, the Bethe-Heitler one, we're actually using some results that were performed through Monte Carlo simulations where protons and photons were interacting and producing pairs. So we use results from Monte Carlo, and we are trying in a tabulated form, and we are interpolating within the code at every time step. So that's one difference compared to others. And similarly about processes number 10 and 11 that you see here, the proton-photon-pion production processes, we rely again on results from Monte Carlo simulations computed with the code Sophia. But again, we use them in tabulated form in our code.
Sophia.
I think this is about it, because we provide also some other details about the decay of particles like pions and neutral kaons, but this is too much of a detail. So I think Matteo now can proceed.
Let kaons go. All right, very
good. So I think I can continue introducing the codes, and the next code I think is B13. So I will present it, even though this is the B stands for, so this is the Marcus Böttcher et al. 2013 paper. So we call it B13. It's a very famous, very highly cited paper. And so we use this code as so this is basically the version of the code used in that paper. And so I was saying I introduced it because it is also very similar in spirit to the Lea Paris code that I will mention later. So both B13 and Lea Paris are are different in spirit with respect to what we just heard, in the sense that they do not solve the differential equation in step by step. So these are not time-dependent codes. These are time-independent codes.
Okay.
In the sense that if we look, for example, at equation 6, which is basically, this
Yes.
is the same equation that we saw before. But as you can see, we clearly put a 0 on the left side. So
Under
we are
steady state.
explicitly, exactly, we are explicitly solving for the steady state, for the at equilibrium between injection and losses. And so instead of solving a differential equation, we solve the integral solution. So the codes compute numerical integrals, which are basically numerical integrals on the injection shape and the various terms for each radiative component. So this is the basic ideas. And so the code, in this sense, it is a bit simpler because it is not as numerically challenging as the time-dependent one. But of course, you lose the time-dependent information. So this cannot be used to study flares, for example, or variable sources. But besides that, the radiative ingredients are the same. So we have the leptonic component, and then we have the hadronic component. Yes. So in the Butcher paper, the hadronic part, which is the one we are interested here, for the leptodonic process, they use the Kellner and Aronian paper, which is again a very highly used result in our field, which is basically a semi-analytical fit to Monte Carlo simulations, which makes the code fast because at the end you are just using a semi-analytical formula that you just integrate.
Yes.
And then the only thing to mention is Bethe Eitler is not included, so this code doesn't include this component, and you will see later when we will show the differences.
That matters and when it doesn't.
Correct, exactly. And then the cascade, it is just computed, I think, iteratively, but the results are, it is this semi-analytical approach which is described in the Bay 13 paper to compute cascade from the secondaries.
Okay.
So then I can continue presenting Lea Paris because it is, as I said, it is very similar, at least from the physics point of view, to the Butcher code, in the sense that it is a steady state solver. So we solve as it is here. It is much simpler at the end of this paragraph. We solve the differential equation equal to 0, and so we reach the equilibrium. Exactly. The only thing which is a bit more specific to our code is that instead of using semi-analytical approximation for the proton-photon interactions, we run the Monte Carlo. So we basically coupled our code to the SOFIA Monte Carlo code. So every time we need to know what is the injection of secondaries from P gamma, we run the Monte Carlo, and then we use the discretized result as our output. It has an advantage in the sense that we are not making approximations there. It has a disadvantage that makes the code slower. And you will also see that it makes the output a bit noisier. So every time you will see the Lea Paris code, you will see the Monte Carlo noise appear. And this is, I think, enough to describe our code. Then in the rest of the paragraph, we are describing what we add compared to this, to the original version of the code, but this is a bit technical, and at the end it is just you are basically improve the code with respect to the published paper of 2015 just by adding the external photo field interaction and the PP as it is mentioned there. So I think the fifth code, it is Lea Mock, and I think Maria can give a summary on behalf of Stamatis.
Wow, that's a word.
Okay. Thanks, Matteo. So Ilhamok is, let's say, the next generation code coming from the group in Athens. Stamatis was my former PhD student, and he developed this new code in order to, let's say, address the problem of the computational cost of Athena. So this code Athena is typically very slow, even though it is accurate, but especially when you want to compute numerical models, that have all these p gamma interactions that were mentioned before, it can become very slow, leading to computation times of a few tens of minutes even. So Matthias wanted to have something which is more user-friendly and also faster, and this is how LeHammock came to became also available. It's an open source code, and it is also available for users who are interested.
Go check that GitHub repo.
Yeah, and so the idea is very similar. It is a time-dependent code, very similar to AM3 and Athena. The main difference is the method that is being used in order to solve this set of partial differential equations. So contrary to what Athena is using now, LeHammock is implementing this finite difference method, which was introduced back in the 70s by Chang and Cooper. The advantage is that this is an implicit it uses an implicit time-stepping scheme. This ensures stability and a shorter computational time.
Yes.
I think this is, and compared to Athena, I have to say, LeHammock also includes more physical processes. It also includes PP collisions, which might be relevant for modeling dense astrophysical environments, also in the vicinity of the AGN. And it has been used in several applications so far, ranging from modeling of time-dependent emission for blazars to GRB afterglow emission, and also cascade emission in current seeds in M87 star.
Very cool. Nice.
And that's all about LeHammock.
Okay. And how did it get that name? Where's that come from?
Leptohadronic modeling code.
There you go.
Yeah.
Very cool. Okay. All right. So we've got our 5 codes, reasonable explanation of what they are, and where should we go next?
Yeah, I think the next point is resolution in codes.
Okay.
This is still a bit of the theoretical part, I would say, because it's not yet about comparing the different codes to each other, but instead to investigate what time resolution and energy grid resolution do to the results. I think to keep it short, we just investigated 2 main points. The first one is the energy grid resolution with Athena. Maria, probably you should present that one.
Okay.
Okay, sure. Maybe the first test was about the energy grid resolution in the codes Athena and AM3. And the second part that maybe Matteo can cover is about the resolution used in the Monte Carlo calculations.
How many?
Just if we want to start with Athena, just to mention that in Athena, there is the possibility to change the energy grid of the particles and photons. But for most cases, for photohadronic interactions, the number of grid points per energy decade, which is this parameter NPDEC that you see there, is kind of fixed. For purposes which I'm not going now, for reasons which I'm not going now to describe, but when we are actually using the leptonic module only of the code, so when we only consider leptonic processes, it is possible to change the energy grid that we use for the electrons and photons. And this is what we saw in this experiment. We saw, and I will let also Annika talk about AM3, we are increasing the number of grid points per energy decade in a particular, let's say, physical framework.
Okay.
Annika, would you like to say something about AM3, and then I could take over to describe the figure?
I think we have actually 2 separate figures here because AM3 cannot change the grid size of the energy grid. The only thing that we can do, we have a relatively high resolution of the energy grid per se already, which is 23 points per decade, with respect to 10 points per decade, which is the more standard choice, I would say. But instead, what we can do is, exactly what you're pointing at is to choose the resolution of each time step. And there is no a priori choice of that. So this is really something that the user needs to do for every simulation, and it's also up to the user to find out the appropriate time step that would not lead to any wrong results, because
convergence.
Exactly.
Show it.
So if we go down, we can see in figures 1 and 2 very nicely how the upper one is the convergence with respect to energy grid. That is the Athena result.
Okay.
Yeah.
All right.
So I will say a few words about this. As you can see, each curve is obtained by increasing the energy resolution in the grid. So going from 5 points to 10, 15 up to 25. And as you can see, Annika mentioned, 25 is very similar to the 23 grid points they're using per decade. So this example here is a synchrotron self-Compton model that has 2 generations of Compton photons. This explains the 3-bump structure. And it is clear that if we look at the photon spectrum on the left panel, by changing the energy grid resolution, you see large changes in the Compton emission, at least, that you get. Even though the synchrotron spectrum, which you can see on the left, the first bump at lower energies, is rather insensitive to that choice, the Compton spectra are sensitive to the grid resolution. And this is kind of expected in our code, because if somebody wants to compute the emission coming from Compton processes, the user has to integrate over the photon and electron distributions. So you have double integrals. And because in our code, these integrals are performed upon the given energy grid resolution, so we don't do any interpolations, this is why you see large differences when you change the energy grid resolution. This comes from the numerical integrals that they are coming into play. The electron distribution function is not so much affected, even if you look at the middle panel. The only thing that changes by increasing the energy resolution is that you capture better the cooling of the lower energy particles close to energies close to gamma of a few. So there, exactly where you point. And lastly, if we look at the third panel, we show on the top how what is the execution time in a single CPU of my laptop specifically.
Oh, your laptop, okay.
This changes with NPDEC, with this parameter. And you clearly see that the trend is stronger than linear on the top. And the top and the panel below shows what is the energy, let's say, density in photons and electrons that you get by changing the energy grid resolution.
Okay.
So clearly, ideally, one would like to find convergence in that and also have a short execution time. So we kind of settle in the choice of NPDEC equal 10 points per energy decade, which is okay. It's roughly similar to the values you get with higher energy resolution, but if you look at the top panel, it is much faster compared to the other, which takes thousands of
more than an order of magnitude.
Yeah. So this is why in Athena we choose NPDEC equal 10. But the user should be aware of these changes.
Yes.
Yeah.
Absolutely. Very good. Nice caveat. Okay.
All right. Then I can take over, and it's the same scenario that we simulated. So the same idea of you have a synchrotron spectrum at the very left, then you have one inverse Compton scattering bump, and then a third and a second inverse Compton scattering bump. Just what Maria said. And as I mentioned earlier, this time we varied the time step resolution.
Mm-hmm.
And this is shown here with respect to the dynamical timescale. The dynamical timescale in these objects, it's just the escape time of particles and the blob size, basically.
R over C or something. Uh-huh.
Exactly.
Okay, I'm following.
Yes, as you, I would say, may expect, the results differ a bit, but what we can also already see is that overall we have actually kind of a nice agreement between the different independent of the time step. So the overall features are always similar.
Right.
I think the middle plot shows it a bit better. We take as a baseline the highest time resolution, and then we compute the deviation with respect to that.
Mm-hmm.
And somewhat similar to what Maria said, in some sense you can see a convergence, in some sense not. But you could see that the purple-ish line is the closest to this green baseline that we have.
Yes.
Looking interestingly, there is somehow the 10 is closer to the baseline in some points at least than the 50.
Well, okay.
So it's not a clear linear process, I would say.
Right.
Then again, on the right-hand side, similar plots, the energy density at the bottom and the execution time on top. You may notice that overall we have execution times that are a factor 10 less, 10 to 100 smaller, which is simply due to the fact that our code is more made for fast execution.
For speed.
Yeah. Okay. I would say in principle, most people, I mean, going below, even having less than even 10 steps per dynamical timescale is never the case. Typically, we settle between something between 10 and 100.
Fair.
That's a reasonable one that we choose.
Okay. Good. All righty. So, was the converted?
Then, if you want, I can move on to the figure 3, which is again, well, it is the last. It is the last resolution effect that we discuss. So this is very specific to the Lea Paris code, because as I mentioned before, this is the only code that is actually running iteratively Sophia step by step. Right. So when before I told you that in our output or in our code, you do see the Monte Carlo noise, you can clearly see. So here we show you the 3 lines. So the red, blue, and green are just decreasing the number of trials. So the number of Monte Carlo simulation every time we call Sophia. Of course, okay, we don't have the plot of the time, but this is clearly affecting the computing time. So you can a much faster code if you run with the green. Yes. But this is also telling you, and this is in practice what we do, that our normalization is fine. So at the end, what we typically do is that we run with low Monte Carlo resolution when we do tests. And then once we are happy, we produce a final high resolution curve, which correspond to the red one. And then the other one, the orange dotted line, which shows you a different aspect. So this is not now the number of Monte Carlo simulations per call, but it is how many proton energy we sample. That's what we call call. So for a given proton energy, we call trial times the Monte Carlo. So in this case, we are, and given that we start from the highest proton energy, if you reduce the number of call, you're basically cutting the low energy part. Okay. This is also showing that if you want, you can speed it up by focusing only on the higher energy part, and then at some point ignoring the low energy part. And if in this zoom in the small subplot, you can see that if you are interested in the peak, at the end you are correctly identifying.
You're doing okay. Okay.
So I think this is all for the resolution part. And then I think, so that was the intro. We are probably running a bit late. Well, now let's see the comparison. So let's see the result. So now
Okay.
let's move to the section 5. Yes, it is.
Yes.
Yes, so I will first introduce what test case we are doing, and then we'll comment on the first figures, and then I will let Maria and Annika continue.
Cool.
So the idea is that, of course, given that the code are intrinsically leptohadronic, so we both have the leptonic part and the hadronic part, we first need to have a look at the leptonic part.
Yes.
No, sorry. Actually, I think it's the previous page, because we need to have a small intro before doing this.
Okay.
Yes, sorry, because figure 3. Yes, okay. Figure 3 was actually in the next page. So if you go to page number 9, there is before. Yes, here. So before introducing before running the simulations, given that the codes are very different in the way they are written, we had to make sure that we were actually comparing the same things.
Yeah, apples to
So the
apples.
comparison have to be fair because the parameters are not identical, are not defined in the same way, etc. So there are two important things. One, it is coming directly from the fact that we are comparing time-dependent codes and time-independent codes. So the steady state. So this already is bringing some kind of difference in the final result.
Yeah.
And so besides the fact that you defined, I think we can ignore the equation 8, 9, and 10 because these are just the way we define the proton density.
Okay.
What it is important is, on the other end, the fact that when you have synchrotron cooling or any type of cooling, time-dependent codes actually track correctly the shape of the distribution at equilibrium. On the other end, other codes like ours, Lea Paris, they force this kind of intrinsic break, and we add it as an extra free parameter.
Okay.
So, and given that, so we can, of course, best guess it, and then have some kind of hard break in our particle distribution, but it will not be exactly identical to the self-consistent cooling that it is achieved by the time-dependent code.
Yes.
This will become clearer later once we will actually see this
You'll
effect.
see the breaks, right?
Exactly.
Okay.
And then the other small thing in the next slide is that, again, it is something that if you don't dig into the code, you will never notice, but it is the very last part. So our code takes into account a correction due to some, basically photon averaging in a sphere, which is this 3/4 factor that comes from 29 paper by Gould. And so that we basically treat it as an homogeneous zone, but then we correct by the fact that you have a radial distribution. And so when we given that not all the codes use this, when we compare, we need to make sure that this 3/4, which is 0.25, when we compare the differences, it's factored in.
Yes. Okay, good.
So once this is all set, then we can start comparing the code. So the first thing we did was indeed to check the leptonic part.
Right.
And we checked the leptonic part because we were hoping to, if you want, define a kind of base level of agreement between the code, and then see how much the hadronic part was differing with respect to this.
Good.
So the leptonic part, in principle, it is easier. As I was saying at the beginning, we can test it with analytical formula. So we were confident that we were something better than the hadronic solutions. So we can maybe just directly look at the plot. So let me first show figure 4. Exactly. So these are typical, let's say, Blazar models in which we see the first bump, it is synchrotron radiation, and then we have the synchrotron Ceph-Compton at high energies. So on the basically all plots from now on, you will see on the top the various codes that have been produced. And on the bottom, it is the difference with respect to the average.
Yes.
So we average all the codes, which we consider this to be the reference level, and then we see how far we are. And this is in a relative, so the 0.1, it is a 10% difference.
Correct. I'm with you.
So you can see that the leptonic part, it is actually pretty good. Of course, we see some discrepancy at the very steep cutoff. But in the power law part, we are basically at the 10% level. Indeed, what you identify there, it is the synchrotron self-Compton, the synchrotron self-absorption, which is indeed more difficult to model. And so you see some differences in the exact occurrence of the cutoff. But then once you enter into the power law part, we are well in the 10% band in the excess. And so we did two tests. On the first one on the left, the Compton scattering it is in the Thomson regime, and then on the right we are deep in the Klein-Ishina to see if the Klein-Ishina effect is also good. And as you can see, it is confirmed. So of course, again, the cutoff when the spectrum goes down very steeply, it diverge, but then it diverge because you are going down basically by 4 orders of magnitude in a very narrow beam. So then it also becomes sensitive to the dimming. But I think we can consider 10% as our level of agreement for the leptonic part, meaning that we can then build upon it. I think it is fair. So I can also maybe quickly comment. So we will not go in details over all the various parameters, but all the input parameter values are given in table 4. So if people want to reproduce the result, this is basically so what I was presenting now were the SSC, the leptonic test, in which people can see exactly what are the values we were using as injection. For in this case only for the electrons. Very cool. And then I can maybe yes. So let me quickly also discuss figure 5 because it shows exactly what we were saying before on the break. So now we show exactly. So now we show it is a comparison of the break for time-dependent codes and steady state. So now on the left, it is the electron distribution, and on the right, it is a photon distribution. So now it is a heavily cooled electron distribution. And you can see, so what a steady state code as Lea Paris would do is the green line. So you have a sharp break happening there between two power law-like regime. But then if instead you have, and you can see the corresponding synchrotron and self-Compton, but you can see that if instead you have a full time-dependent code, the break, you see the break, but it is much more smoother. And so this would also, so you would see differences in the photon distribution, not coming because if you want, the radiative part is different, but because the input, so the fact that the break is sharp, it is causing this difference. So this is something that we need to take into account, because we will also see this effect when we will discuss the hadronic comparison. So we need to make sure that we know where the difference is coming from.
Very good. Okay, I'm with you. Good.
So I think this is done for the leptonic, and then finally let's have a look at the hadronic comparison. So Annika will walk us through.
Happily so. So let's finally get to the hadronic scenarios, and I'm going to start with some more academic examples. So what you saw before that Matteo presented, you already saw the luminosity in the observer's frame and very like real life kind of scenarios that were shown. For the hadronic, where we expected more differences because it's just a lot more difficult to implement. And you heard about the Monte Carlo simulations that are run. And for example, we use an implementation where those Monte Carlo simulations are processed and then a semi-analytical approach is produced. So we expected a lot more differences. And in order to investigate those, we first went for very academic examples. So for a monoenergetic proton distribution, interacting with a gray body photon field, where you just specify the temperature and the energy density so that you can clearly see the effects that you have if one single proton energy interacts with these photons. And
that's a great test. It's a great test.
The results of this exercise are shown in figure 6 exactly, which we can have a look at.
Good. Let's zoom out and get it all.
Yes.
Okay. Right.
In comparison to what you saw earlier, which was the observed luminosities, here we show the co-moving production rates.
Yes.
So from top left to bottom right, we see the production rates of photons from photopion production. Then we have, and here photopion production, you go through the pion decays, and then in the end you get some photons, right? So you have the full decay chain that is already in there.
Yes. Yes.
The same pions can also produce neutrinos, upper right, leptons, lower left.
Yes. Yes.
And all of this is the photopion production, and then on the bottom right we have the photopair production.
Yes. Okay. I'm with you.
If we go through it, let's just mention some interesting aspects.
Yeah.
If we go to the upper left plot and you zoom in a bit, you can see that, for example, the AM3 code here has this bumpy spectrum. This is simply due to the fact that the interactions with the model that we use relies on discretizing the interactions into different channels, production channels. And each of these bumps just represents one interaction channel. And this also explains why it's cut off at a lower energy, because we just never reach the next channel with this monoenergetic protons and the gray body photon field.
Sure. Yeah.
As we will see later on, this disappears if we have a more realistic scenario of broader distributions.
Yeah.
Because, this is also what the model was developed for initially. We can see overall that for the photopion production, we have already, I would say, relatively nice agreement. Again, the bottom panels show the deviation with respect to the mean of each figure, of those production rates, and we see that we are plus minus 20%, which is actually pretty good.
Considering all the different assumptions that are going in, so 40% spread total. Okay, fair, good.
If we quickly look at the photopair production, which is the bottom right plot, which is a completely different process, so completely different implementation for all of the codes. We see a bit of a higher discrepancy for this one in this exact scenario. I think here this is a good point to mention our appendix, because we have a very thorough investigation of the effect of the energy grid on the results of Athena, especially in this case, where we can explain why these spectra are so much higher for the Athena code with respect to the other ones.
Good. So check out that appendix, people.
Now going to the next figure. It's a lot larger spread.
Larger spread, about 60 plus minus. Okay. Let's go to figure 7, which is going to be similar, but this is
similar. Exactly.
This is not monochromatic. Okay.
This is not monochromatic. This time we use the somewhat most realistic academic example of power law and power law. So you have a power law distribution of protons on a power law distribution of photons. And we can, in principle, I would say, same thing. The spectral shapes are very well covered. We have some discrepancies for some of the models, but overall we are plus minus 20% here. Exactly. We have the Athena code that produces a bit less. Overall, maybe to mention, maybe you would expect that some differences average out with the power laws with respect to the monoenergetic ones. But what actually also happens is that discrepancies accumulate.
Yes, I was going to say. Yeah.
In contrast to what one would expect sometimes, that it all averages out, this is not what we see.
Okay. Each one is low. Oh, yeah.
Yeah, exactly. Or you may have effects from both ends of the spectrum that can still accumulate.
Okay, true. Okay,
Yeah.
cool. Okay.
But in principle, what we maybe something nice to mention about the beta Heitler production here, that we have, you may remember that the Athena code showed these very elevated profiles on the bottom right in the previous one.
Yes.
This effect actually disappears if we consider power law to power law, which is a positive result for us. Here, the large discrepancies indeed disappear.
Yeah. Now we're not plus minus 60% anymore. Okay.
Yeah.
Okay. Still in the total 40% spread range.
Yes.
Good. Awesome.
I think with that, I would conclude and hand over to Maria, who will summarize these results with the energy densities or total energies.
Just a quick note, if you go now to figure 8.
Yes. Good.
Note figure 8, which is another colorful diagram.
It's beautiful.
But we tried here, instead of comparing the differences across energy, just to look at the integrated quantities of these two hadronic academic examples. On the top, with the monoenergetic proton interacting with the gray body field.
Mono. Power law.
And below the power law case. And each, let's say, set of histograms represents what is the energy injection rate in some units for the different channels that you can see on top. For example, if we look at the left, on the left, we see the energy injection rate into gamma ray photons because of pion decay. And for this particular example, you see that there is somehow a decreasing order in terms of the code results. So LHAMO here produces the least of the energy injection rate compared to AM3, which has the highest. Yes. But if you compare now the same, this kind of ordering is not universal in a sense, because if you look what happens into the energy injection rate of pairs, the differences are more random, and also for the Bethe-Heitler pair injection, as we saw before in this example, Athena was overestimating, and indeed it overestimates the total injection rate. The difficulty here is that we don't see a clear trend, so we cannot say for, even if we use the extended power law cases, you see that all these relative differences change across time. And this was one of the difficulties that we encountered, and it's very difficult to explain. It would, if we wanted to provide to the users, let's say, a clear, I don't know, message saying, okay, this code overproduces, for example, by this amount.
The other thing, right?
We would need a huge scan of the parameter space, which was not in the scope of this paper. But just to show you that overall, we have factors ranging differences in the total energy injection rate between 2 or 1 point something codes. Keep in mind, though, that these are energy injection rates. So differences might become larger when these particles are left to radiate.
Yes.
Especially if radiation processes like Compton scattering, which depend on photons produced by synchrotron photons produced by the particles, might accumulate or might depend on the square. So these relative changes might become larger for certain parameter spaces as well. So I think that's the main message that we would like to, for the readers to take away from this plot. And then I think Matteo can say something about our next results, which are leading figures.
Yeah, exactly.
The more realistic ones.
And continue. So the next in our mental flow, the idea is to have leptonic test and then test with some kind of, as Annika say, academic or let's say test case.
Idealized. Let's just call it idealized.
Idealized test, so monochromatic or power law. And so here the final test one was to produce something which was more as we would observe. So it's what we called Blazar-like solutions. So we did two tests. So let me show you. The first is one in figure 9. It's what we call a proton synchrotron. So again, if people want to reproduce, all the parameters are in the table.
Cool.
So in the proton synchrotron solution here, so the first bump is electron synchrotron. The second bump is the famous proton synchrotron. And then the high energy components are the secondaries by proton-photon interaction. So there is this weird tail, which is Bethe-Eitler, and then there is the pion injection. This is the pion injection. And so now we compare, as Maria was saying, the final photons that the observer would detect. And so we do expect indeed that the differences that we saw at the injection rate open up, because then we have other stuff that can enter in, and so the errors might indeed open up. And so we do see it. So now if you look at the various successes or differences between code, you can clearly see that it depends on the radiative component. So you can see that, for example, the electron and proton synchrotron are actually rather good within plus minus 20%.
Right.
But then what opens up is the Bethe-Eitler, where it explodes.
Yes.
Is the Bethe-Eitler part. So I think this might also be a bit, well, I call it unfortunate, because as you can see, for this model, we don't see the peak of the Bethe-Eitler. We see some kind of the falling tail of the Bethe-Eitler component. Yeah. So it does open up between the different codes. Yeah. But okay, I mean, if you look at the scale down, we are at plus minus 0.4, 0.5 in the world.
Yeah, in this region there.
Yeah, in this region there. Yeah. And then the pion bump, the last bump, it is again within 0.4, let's say.
Yes. Okay.
So this is for the photons, and then on the right for the neutrinos. And as you can see, the neutrinos, given that they are directly, well, they don't do much. So once they're produced, they go to the observer.
They escape.
So they seem cleaner. And as you can see in this test, at least the neutrinos are within plus minus 20%. Again, the Q, the rapidly folding Q, they diverge. But then this is it. One thing that I didn't, probably we didn't mention. So here you see the 4 codes, and then the dotted line, it is actually the result from the analytical neutrino approximation. Okay. So this is something which is done or semi-analytically, just by considering the proton distribution and the target photon field, and then computing the neutrino output. And as we can see, okay, of course, it is a bit off. It is worse than what we would get from the full numerical simulation, but it's not that much. In particular, the peak, it is at the right luminosity and energy. Yeah. Then the shape of the cutoff, it is approximated, and even at low energy, it falls a bit below. But I think that we can say that as a shape, it might be a best.
As a morphology, it's A-okay.
And so then the other test we did, it is the one at the bottom. And this is what we call a LIA, so lepto-hadronic scenario. So it is a scenario in which you have both leptonic and hadronic processes in the gamma ray band. So now if we go from left to right, we have again electron synchrotron. Then we have the small bumpy stuff. It's the Bethe-Eitler, and then here, and then you have the synchrotron Self-Compton there.
Yes.
And then you have the pion bump at the highest energies.
I'm with you. Thanks for describing
and
that.
So you can see that here as well, the differences depend a lot on which process is dominating. Again, you have the Bethe-Eitler, which is opening up a bit in spread. And then you also have the pion bump, which is opening up a bit. It's opening up quite a lot. So maybe, I can comment a bit on this. In this case, for example, the green part is the Lea Paris code, which is overshooting a bit the others. But it's one of the good test, because if you look at the synchrotron component, this is exactly the case in which for our code we need to force a break.
Yeah, you mentioned that. Yep.
And so you can see that the shape of the synchrotron component, it's a bit weird. And so this could explain a bit why we overestimate the neutrino production, and so the pion production, because the target photon field is not the same. And you can see the same behavior on the right for the neutrinos, in which again the layer pulse opens up quite a bit. It reaches plus 0.5, 0.6. But part of it should be at least due to this different shape of the
way that's handled, right?
And here again, you can see the analytical approximation with which I think we can say that it tracks well the peak, and then it falls a bit off for the low energy and high energy part.
It's narrower overall.
Yeah.
Cool.
So I think this said, we can move to the next session, and I think
I can take over. Yes. So you may think that what Matteo was showing is the end of it, because this is what we actually wanted to compare, the Blazar spectra. But no, we have a section called Other Scenarios.
Indeed, you do.
And the idea behind that was to look at scenarios that can only be interpreted or looked at with the time-dependent codes, because what you saw so far, you saw Matteo's results along with Maria's and mine. So that means that steady state and time-dependent codes can all run it. There are, however, some cases, some scenarios that are not linear, that in this sense cannot be modeled with a steady state solution.
Yes.
And the first one that I'm just going to quickly introduce is the inverse Compton catastrophe. You saw the plots already because we had shown them for the time and energy grid resolution. That was exactly the scenario. And the idea is that you have one synchrotron peak, then a first Compton peak, so which would be the two bump scenario that Matteo's code could still really nicely do. But then this inverse Compton peak again scatters and produces a second inverse Compton peak.
Yes.
And this is the nonlinearity that cannot be reproduced unless you have a time-dependent code. So this inverse Compton catastrophe, we investigated with Maria's code, the Athena one, and AM3. And I think we can go quickly over the figure that is possibly... Yes, on the next page. The overall executive summary is that we find really nice agreement.
Both that's a great summary.
on the energy, on the energy distribution of the electrons, that's the left upper panel, as well as the luminosity of photons.
SED here. Okay. Yeah, very good. Oh, very good. Yeah. 5%-ish or less.
Yes.
Really?
So even though this is a nonlinear process, it's quite remarkable actually that we find such nice agreement.
What is this gray box? That must be
the gray box here is the energy range of injected electrons.
I did get it. Okay. Good.
You did? Wow. Well, very nice.
Yeah. Okay. Good. Well, that's a great bottom line for this one. So. Cool.
And I think I can hand over to Maria, who's going to introduce a hadronic nonlinear scenario.
Yeah.
Right. So now moving to the final testing case, I would say. This is about nonlinear proton cooling, and it is known in the field, let's say, with the name pair production synchrotron loop, or for short PPS loop.
Okay.
So a few words about the physical scenario. Look at the results. So this was proposed back in the 90s by Kirk and Mastichiadis as a mechanism for releasing energy in a fast way from protons and explain its three layers. So the idea here is that you have some protons that are charged particles, and they are found in a region where some in a magnetized region. So they're going to produce first some synchrotron photons. So the same protons can interact with the photons via Bethe-Heitler pair production and produce electron-positron pairs. Now, if the magnetic strength is such so that the generated pairs emit their own synchrotron photons in a specific energy, then protons will also interact with the synchrotron photons from the secondaries. Then they will produce more pairs. And this forms, let's say, a cascade, a runaway process that drains the energy from the protons through the Bethe-Heitler process. Very interesting, and this is the summary plot, figure 12, where we show different types of things. But the concept and what has been shown using analytical arguments in that paper, it is that this creates an instability in the system, and the system behaves. The system, what I mean, system is the protons and the photons behave as an oscillator that oscillates in a characteristic frequency, and this is a very unique property, let's say, of dense proton-photon systems. So let me show you, and we were pretty amazed when we saw these comparison results with Annika when we did this kind of experiment, because it is the first time that we actually verify the findings by Kirk and Mastichiadis with another code besides our own, besides Athena.
Very cool.
So what you can see on the top left panel are photon light curves in some arbitrary units for different choices of the proton injection rate in the system, again in some arbitrary units. And what you can clearly see from these solutions now, Athena are the dust, solid are from AM3. What you can see is that by increasing the proton injection luminosity in the system, going from green to purple, at some point you see a change in the behavior. So for the green curve, the dark green curve, for the lowest injection rate of protons, the lowest one, yields a photon luminosity which actually tends asymptotically to a constant value if you look at the green curve bottom. Then if you increase the proton injection rate, you start seeing that the photons are actually exhibiting flares in a quasi-periodic way. And so this marks this transition from the linear to the non-linear cooling of protons, and where the system behaves as an oscillator. What you can see also on the bottom left panel are two snapshots of the photon spectra. Again, arbitrary units.
The flat
here,
yes, I'm with you.
So essentially what you see is that for the case, these are photon spectra that correspond to the purple light curve on top.
Yes, 2.2.
So purple, So the dust lines in the spectra show the, let's say, the spectra coming from coming at early times before the first burst occurs. And what you can see here is that we can identify the proton synchrotron component, which is around 10 to the minus 6 in these units, it peaks, and then it is followed by the synchrotron emission of pairs.
Zinc.
But then what we actually see at the time of the first burst, we see an increase in the luminosity. So we see the spectra having a higher luminosity, higher normalization. And also you see a different shape. So essentially what actually we find, and there is a pretty good agreement between the two codes, is that not only we see changes in the photon luminosity, which are captured by the light curves, we see changes in the spectral shape as well. And both codes capture that as well.
Nice.
And keep in mind that this process is kind of initiated by Bethe-Heitler pair production, and we saw that there are some cases before that the Athena code might overproduce the injection rate or not. But here we clearly see that the two codes agree, for example.
Cool.
And the most amazing thing I have to say is that both codes capture the periodicity very well.
Yes.
And the evolution of the period with time, because this is not an oscillator, it is a quasi-periodic oscillation that it is being produced.
Ooh, QPOs.
On this panel that we are showing here, we simply compute the derivative of the light curve that enhances the periodic signal.
Correct.
And we see that both codes actually capture that very well.
Very good. Yeah, they do amazingly well, actually.
Yeah.
Very
Below and in the rightmost panel below, you can see the evolution of the period with time or with the number of cycles
Right.
for different proton luminosities. The evolution is very similar with both codes. And yeah, just as a final note, this is the very first demonstration of this PPS loop instability with another code besides Athena. So it's has been beautiful, yes.
It is beautiful. That is
And
awesome.
with that, I think Matteo would like to say a few words.
Or if you want to finalize, I
Or
think it's time for
finalize?
the conclusion. Yeah, go ahead.
Yeah, maybe we can say just a few make a few concluding remarks. So we hope that we demonstrated how the different codes behave in different parameter regimes. We saw that the agreement is very good at the level of plus minus 10% when we consider only leptonic processes,
Right.
like synchrotron and synchrotron self-Compton models. When we move to more complex models that incorporate P gamma interactions, the agreement actually becomes worse. We have agreement at the level of 20, plus minus 20 to plus minus 40%, which depends on the energy range. So this is not a global, universal, let's say, relative difference.
Right.
It is very promising that different codes that have been developed with different numerical algorithms can still recover the basic features of the Blazar SED. And also we have a very good agreement in plus minus 20% for the neutrino spectra, which is also very important now in the era of multi-messenger astrophysics, where we are trying to explain potential neutrino associations with blazars.
Ice cube, pay attention. Very
cool.
Very cool.
Yes, and I think this kind of work also, after the end of this work, the AM3 code also became publicly available. So it is the second open source code that there is in the market, and is also very widely used. And there is a effort of actually making our codes publicly available for the community.
Cool.
And also, we hope that this work will also provide, let's say, a benchmark for other codes that might be developed in the future.
Yep. Very cool.
Final note from my point of view, this work has been very instructive for us, but it is also tailored for AGN modeling. So it doesn't cover the full parameter space. Which might be relevant for GRB physics, for example, or other compact scenarios for coronae, which also are now very popular with the NGC 1068 and IceCube neutrino associations.
Right.
So this might be something that we could consider in the future, like extending this code comparison, if not with the 5 codes, with a subset of the codes or with new codes to another parameter space.
Very cool. Beautiful. Beautiful. Matteo, Annika, and Maria, I want to thank you so much for walking us through your article. It had quite a gestation period. So, yes, thank you so much.
Thank you very much.
Yeah.
Very much.
Yeah. And you kind of mentioned it a little bit there. So I'll just, ask you to, push a little bit on it. Where do you think we go from here in sort of the immediate future, given the published article? You mentioned there toward the end, this is only AGN, and there are certainly other objects, GRBs, etc., TDs maybe in some level, kilonova, that where comparisons could be of interest on that. And so just a little bit more on where do you think we go from here, given the published article?
Well, maybe I can start. So I agree with with what Maria was saying. Actually, when we started, I think even at some point our title of the paper was part one. Then we
Right.
remove it because
Yeah.
we weren't sure what we were going to go. But it is true that when we started working on it, we have seen it, especially because we see differences that depends on the parameter space. We can't make a global claim on the differences between the codes. In the sense, we cannot say with this magnetic field, with this proton density, this is the difference. This is the systematic you might get on the modeling. And so it is true that then if you want to go to GRBs or if you want to go to Corona, AGN Corona, then well, maybe the discrepancy is less, or maybe it is more. We don't really know. So I think the first step would be indeed to maybe apply this to other specific tests. And I think the GRB were the first thing that we wanted to have, and might be the next natural step. Keeping in mind that, for example, given that it was tailored for blazars, we only included p gamma interactions. So we don't have proton-proton interactions. We didn't test. So
Right.
it is true that they're available. So typically we don't have that many ways to model them, but PPE were not tested here.
Okay.
So I think that definitely opening up the parameter space is probably the next thing we should do.
Yeah.
And then, as Maria was saying, other people wrote other codes, so we could also add. Now more people are adding codes, so I think, and more of them are public, so we could also open it up.
Which is always a good thing. Very cool. Well, it'll be really exciting to see this work take seed and have it develop over the next couple of years, and have some of the other codes pick it up, and in the future as well. Let's say 20 years from now, this will be a benchmark study. How about that? So it's very cool. All righty. Matteo, Annika, Maria, thank you so much again for walking us through your very lovely article.
Thank you very much. Thank you for the invitation.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye, everybody.
Bye.
Bye.